I have written this paragraph here about energy, but for the sake of time, I would like you to read that for yourself, such that we can go straight into the subject matter. So we're talking about energy changes in chemical reactions. Energy is defined as the ability to do work. There is what is called the law of conservation of energy. This law states that the amount of energy in the universe stays constant. Another expression for this is that energy can neither be created nor be destroyed, but it can be transferred from one object or place to another, or it can change from one form to another. There are different forms of energy, you know more than I do, and we have listed a few here: kinetic energy, potential energy, light, thermal, electrical, sound, heat, and nuclear energy. But now we would like to talk about energy transformation as happens during chemical changes. So to start this discussion, we would like to ask this question: what types of energy transformations take place when a flashlight is being operated using electrical cells? The answer to this is chemical potential energy in the cells is changed to electrical energy, which is then changed to light and heat energy in the bulb or lamp. What type of energy transformations take place in your body that allow you to walk? You can answer that for yourself. Enthalpy change. The reaction between magnesium and hydrochloric acid can be represented by the following chemical equation. We have seen magnesium is reacting with hydrochloric acid to give you magnesium chloride and hydrogen, and energy is liberated. Sooner or later you'll be told about something called chemical system. The chemical system reactant here is made up of magnesium and hydrochloric acid. The energy produced is called the enthalpy change for the reaction, and it is a difference between the enthalpy of the reactants and the enthalpy of the products, and it is represented by this delta H symbol. Anytime you see this delta H symbol, it represents a change in enthalpy of the system. It is very difficult to measure the total energy of any chemical system, as this would entail finding the energies associated with lots of stuff: the nuclei of the atoms, the chemical bonds of the compounds, the electrons' movement within the atoms, the various motions of the atoms of the compounds in the system. But scientists are only interested in a change in enthalpy of the chemical system. This change in enthalpy is manifested as either a flow of heat from the system into the environment, in which case there is a noted initial rise in temperature of the system, or a flow of heat from the surroundings into the system, in which case there is a noted initial drop in temperature of the system. Now we'll talk a little bit about exothermic change. An exothermic change is one in which heat flows from the system into the surroundings, and the enthalpy change is given a negative value. So whenever there is an exothermic change taking place, you're going to see a delta sign here, and it will be followed by some value. We don't know what it is, depending on what the reaction is, what the change is. That amount of energy will be produced, but you're going to see this negative sign in front of that. So anytime you see this delta H with a certain value and a negative sign, note that it is representative of an exothermic change. Endothermic change. An endothermic change is one in which heat flows from the surroundings into the system, and the enthalpy change is given a positive value. Whenever you see a delta H sign like that, and you see a positive sign in front of a certain value, it means that that is representative of an endothermic change. We will now look at the theoretical perspective of energy changes in chemical reactions, and this brings us to what is called bond energy. We have already spoken about this in a previous video when we said that when a chemical bond is formed, energy is liberated. For example, when two hydrogen atoms react to form a molecule of hydrogen, energy is liberated. Specifically, if you have 2 moles of hydrogen atoms reacting to produce 1 mole of hydrogen molecules, then that amount of energy is produced per mole of bonds that are formed here. There's something about covalent bonds and their stability. The more stable a covalent bond formed, the more is the amount of energy that is liberated. For this reason, bond energy is defined as a measure of the degree of stability of the covalent bond. To break a bond, energy is absorbed. So you go back to this equation again, you can see that when 1 mole of bonds is formed, that amount of energy is liberated. And to break those bonds, we must insert the same amount of energy that was produced when a mole of these bonds was formed. This table here gives the values for a few different types of bonds, but you can see here that the bond energies are represented, but they are not given either a positive or negative sign. That is because we have to put bond energy in a certain context. If a bond is being formed, then a negative sign is placed next to the value there. If a bond is being broken, then a positive sign is placed next to the value there. Secondly, you can notice that double and triple bonds are more stable than single bonds. If you look at carbon-carbon single bond there, recall that it's only a sigma bond that's present. Look at what is happening in a carbon-carbon double bond. It's much higher than this one here. That's because now there is a pi bond in addition to that sigma bond. And again, if you have a carbon-carbon triple bond, it's even higher than the double bond there because of the extra pi bond that's present. Now we can show how a difference in bond energy between reactants and products can be used to calculate the enthalpy change of a reaction. And the reaction that we were talking about here is the burning of methane in oxygen. When methane burns in oxygen, it produces water and carbon dioxide along with energy. We do not know how much energy is produced, but if we know the bond energies of all the bonds that are associated with the reactants and products, then we can find the difference in bond energy between the reactants and the products, and that will enable us to find the enthalpy change for the reaction. This is what happens in chemical reactions. For this reaction to happen, these bonds here must be broken such that the individual atoms are freed up to form new combinations. How many moles of CH bonds do you think we need to break? You can see every mole here has 4 moles of CH bonds. Every mole of oxygen has 1 mole here, so we need to break 2 moles of that. Every mole of water molecules has 2 moles of OH. So if you have 2 moles there, you're going to have 4 moles of OH bonds being formed. And every mole of carbon dioxide molecules here has 2 moles of CO double bond. So in the end, this was going to happen. We'll have to break 4 moles of CH bonds, 2 moles of OO double bonds, and we'll end up with 4 moles of OH bonds and 2 moles of CO bonds. The same thing is written here. Okay? So these are the 4 moles of CH bonds. We have to zap that. So when we break those bonds, we'll end up with only 1 mole of carbon, but we'll end up with 4 moles of hydrogen atoms. When we break these, we'll end up with 4 moles of oxygen atoms. So how do we calculate the enthalpy change for that reaction using bond energy? And this is how it is done. We know the bond energy for every mole of CH bonds, but since we need to break 4 moles of that, take the bond energy and multiply by 4 moles. And that gives us 1650 kilojoules of energy. And you can see we have a positive sign here. Why we have a positive sign? Because we are breaking bonds, and that will be an endothermic reaction. we need to break 2 moles of oxygen double bonds. This is the bond energy associated with 1 mole of oxygen double bonds. You have 2 moles of that, then you end up with that value there is positive because it's an endothermic change. Adding these two values together, we have this total amount of energy that must be used to break all of those bonds. Now we're going to see how all of these atoms they recombine to form the products. So we now calculate the bond energy of the products. So this is the bond energy that's associated with OH bonds when they've been formed. That's why now you're going to see a negative sign here. In the previous case, we didn't need to put in any positive sign there, but we left it like that because we know leaving it like that represents positive, right? But specifically in this case, we needed to show the negative signs. When you do the calculations for the formation of 4 moles of OH bonds, that's what you get there. For 2 moles of carbon-oxygen double bonds, we ended up with that value there. Adding these together, that's the total amount of energy that's liberated. You can actually know what's going to happen. We use that amount of energy to break the bonds of the reactants, but that amount of energy is released when products are formed. So how do we use these two values to calculate the enthalpy change? There are 2 ways of doing this. One way is by taking the algebraic sum of the bond energies of the products and reactants. And that is it. You can just add these together. That is what is it for the products. Add it to that of the reactants and you end up with this negative value. Or another way would be to take the absolute value of the products and from that subtract the absolute value of the reactants. When you take that one there and you subtract that one there, you end up with the same value here as you got in this case here. 2 things to note. We're noting how the bond energy of the products, which is this, is greater than the bond energy of the reactants by this value. That means that the products form more stable bonds than the reactants. And it is because of that, that amount of energy will be liberated.